Michael. Um, I know yesterday or on Wednesday when I had the interview, you had asked me how it went, and I thought it went okay. But then there was that one question where I realized later on, hey, I think I'm misdrawing the plant in the control block diagram, and I've just been embarrassed about that. And I think it was the first question they asked, or one of the first questions, and I was doing it on Paint, and I was reluctant to do it. I just feel very embarrassed that it's eating me up that I just fumbled it a little bit. And I guess this video is just a vent, to you. I don't need you to submit this to them or anything, but I just need to give myself some ease to show that I can answer such a basic question. I remember they were asking, draw a PID controller, and I started drawing it. I labeled my input as U, whereas U is generally the control law. I should have written R as is customary for a set point or a reference trajectory, but and then I just sort of half did it and didn't draw the plant part of it, and I was just like, later on I was like, what did I do? So I mean, just to show that I know my ABCs and controls, I just wanted to show you that normally you have a input R goes into a controller, the controller. The output is generally labeled as U. Then you have a plant model or actual physical plant, and the output is your Y, the sensor feedback, and these are your sensor or any estimation filter, whatever you have. And then there's a summation junction where the difference is the error, and so between what's entering the controller is your error. And then you might have disturbances, sensor issues and whatever, but let's not consider that for now. But the U is the control law, and it's a function of error. So in the case of a PID controller, it is K proportional, K derivative, K integral, where each term is multiplied by the error, the rate of change of the error, and the integral of the error. Generally, U is Kx, or negative Kx if it's like an opposing force or correcting force. And that K could be calculated depending on the control method you use. So in the case of MPC, it's calculated based on your time horizon or prediction horizon or other means. It could be, bang bang, sliding mode control, whatever. What I've specialized in mostly, especially in my master's thesis, was nonlinear control. So that U is a control law that guarantees the stability criteria of the system, where the Euler-Lyapunov function is always positive and its derivative is always negative. And in that sense, the interpretation we use in this is modulus control is the function V equals whatever is actually the function of a 3D parabola or paraboloid. So you have like imagine this is a 3D parabola, right? This is your Z or V axis, so V equals whatever. It's a function of your state and the time derivative of your state. You have the coefficients of the equation of the paraboloid is can be used as a tuning variable. So basically any state you have is a point on the surface of the parabola. Its projection onto this plane here is the phase plane, and this is why Lyapunov control is also called adaptive sliding mode control. And what you're doing is you're pushing this point towards the origin, and so we know the definition of a equilibrium point is where the x and x dot is equal to 0. So whatever you're doing, in other words, you're driving this point towards the vertex of the parabola. In actuality, that may not give you the minimum fuel trajectory. In most analytical systems, your paraboloid intersects into the face plane. So that looks like at the intersection, it looks like a circle. So that is known as a limit cycle. You may have stable manifolds elsewhere in the phase space approaching this. The fixed point may be unstable, or maybe, divergent, so that your state tends to go towards this limit cycle. In most space applications, in orbit, you don't drive a satellite to the center of the Earth. You're in an orbit. L4 point, even L2 point, you may have a halo trajectory that's minimum fuel, and so we're often controlling for reference trajectory based on the solution to the differential equation of motion, and that's the goal of control theory. So in conclusion, my assessment, my personal definition of control systems is